The first time we quantified acid base is the litmus paper. I guess everybody have done this in your Gen Chem experiment. The really important thing is actually starting from here. After we start to define this value pH, okay, we have a very quantitative way to know the solution is actually more acid or more basic. That's the quantitative definition of pH. So you measure the concentration of H+, which is actually proton, not hydrogen, inside your solution. You take the negative log of that quantity, and the value you get will be the pH. In your water, H2O liquid, it can undergo the H+ and the OH-. You only have a very small portion of that happen because we know the pH of your water is 7. That means the proton concentration inside your water solution is 10 to the -7 m. You know the proton concentration inside water is actually extremely low. Inside your water solution, majority of the water existing as H2O molecule is neutral. And only very small portion of that water will become H+ and the OH-. Right? And the H+ concentration and the OH- concentration is equal to 10 to the -7. The dominant species is actually your water molecule, H2O. But you also have some little amount of H+ and the OH-. It is those H+ contribute to your pH. This is actually a very important concept that you should know. And then if you have acid, that means the pH is smaller than 7. If it's actually larger than 7, it is basic. If pH equals to 7, we call you have a neutral solution. And then if you have acidic solution, that means you have more protons than the hydroxyl anion. If you have a base, that means you have higher concentration of OH-. So this acid-base concept become very systematic introduced by the two scientists. Of course, Arrhenius is actually the one that defined the acid-base the first. He defined the acid as a species that can generate excess H+. We call it species as acid. And then if the things, once you throw into water, it produces excess OH-, then it defines that species as a base. For example, if you throw in your HCl into water to form the HCl aqueous solution, HCl is going to produce H+ and Cl-. Since you throw in HCl, you actually produce more H+ inside your water. Then we call the HCl as an acid. If you throw in your sodium hydroxide into water, that is going to produce more OH- inside your water solution. Therefore, based on Arrhenius' definition, sodium hydroxide it is a base. But very soon, scientists found that's actually a limitation. Because this limits, you can only define the pH inside your water solution. But when we do the organic experiment, okay, you realize most of the experiment you did is not actually in aqueous solution, right? It's always in the organic solvent. Okay, so we need to have a better definition for the acid base. That's why we have this Brønsted-Lowry theory. Okay, so he defined the acid as a proton donor. That means it's going to give out a proton to some other partners. We then call it that species as an acid. In contrast, for the base will be the proton receiver or the proton acceptor. So the guy who accepts the proton will be defined as base. For example, if you have an HCl plus H2O, and then you produce H3O plus and the Cl-. You can see your HCl become Cl-. It means it gives out the protons. So this is actually a proton donor. Therefore, we say HCl is actually an acid. On the other hand, if you look at this water goes from H2O to H3O plus. It actually receives the proton. Therefore, the water will be the base. When I write these equations, those equations on the reactant side, you already have the acid and base. Another example, if you look at this equation, you will realize your NH3 become NH4 plus. You actually receive one proton. Therefore, this will be defined as a base. For your H2S, it becomes SH minus. Guy is actually losing a proton. So this is actually a proton donor. Therefore, the H2S is an acid. This table summarizes all the things we say. In the Arrhenius acid-base theory, the way you define acid-base is really depending on what species you generate. You generate H plus, you are actually acid. If you generate OH minus, you are base. If you have aqueous solution. However, to make the things more general, Brønsted-Lowry provide another theory. It defines the species that provide H plus as an acid, the species that accept H plus as a base. This is actually the concept that we're going to use a lot in this chapter. We're going to expand this concept a little bit more so you can actually bring up the concept of conjugate acid and base. Assuming there's an equation HA plus H2O that give you H3O plus and the A minus. Based on the Brønsted-Lowry theory, you should be able to actually define what is acid, what is base. HA is a common bond that we use to represent the acid. After reactions, you go from HA to A minus, so you lost proton. Therefore, we know this one is actually acid. And then for your H2O, when you go from here to here, you receive the proton. Therefore, this is the base. The interesting is actually once you write these things down, and then once you put on this equilibrium sign, all the things we described was based on the reactant side, right? If you go from reactant to the product, then you can define your acid and base. But if we actually now look at from the product side, a similar thing is actually going from your right to the left. This guy, when you're going back to here, he actually lost a proton. Based on definition, this will be a proton donor. Therefore, this one is actually acid. For this guy, go back to here, you go from A minus to HA. Therefore, this one is actually a base. We create another terminology. Call this guy as a conjugated acid and this guy as conjugate base. So for all the acid-base equilibrium equations, we can always find the acid and the conjugate base pairs. In these specific reactions, you have actually two conjugate acid-base pair. The first one is HA, A minus. The other one is actually H2O and then H3O plus. So these are the two conjugate acid-base pair. In this case, we'll say the HA is the acid, the A minus is its conjugate base, the H2O is the base, and the H3O plus is the conjugate acid. The way you find out your acid and the conjugate base, they always follow this relationship. Your acid is going to equals to your conjugate base plus the H plus. So let's give you one example. If this is actually equation you see, can you actually define the two acid-base pair? From here we know this and this. Apparently it's actually a pair. This and that is another pair. So if you go from here to here, it actually lost the proton. So we know this is actually defined as acid. And this one will be the conjugated base. If you go from here to here, we know this is actually obtain a proton. Therefore, this is actually a base, and this will be the conjugate acid. Another very important concept you should learn from this equation is that this is actually not an equilibrium equation. This single arrow means the reaction is going to move toward the product side. The question you're going to encounter will be, you have two acids inside your system. One is this guy, one is that guy. So the question will be, which one is actually a stronger acid? This one should be actually the stronger acid because the reaction, because it's stronger, that means actually the reaction is going to occur to the product side. So this one will be the stronger acid. The very important implication from this example is that the H3O4 is actually a stronger acid than your H3SO4 plus. So you can consider both acids want to release the proton. Whoever is stronger will win the battle. If you win the battle, it means actually it's going to move from the current position to the product side. If this is stronger, then we know the reaction will move to the right-hand side. If this one is stronger, it should move to this side. But the fact that inside your chemical equations, it indicates the reaction is actually move toward the product side. Therefore, we know this guy should be the winner. So HCl4 will be the stronger acid. Another example is this. HNO3 plus F minus. That give you NO3 minus plus HF. Again, you see this thing says the reaction is moving toward the product side. By now, you should be able to see this. This is actually acid. This is conjugate base. That is base. That is the conjugate acid. Therefore, two acids appearing inside your solution. Which one is actually a stronger acid? Yes, HNO3, right? Because the reaction is actually moving toward the product side. Therefore, that's actually a stronger acid. Let's summarize these things. Okay, we know the acid-base pair is HNO3. Conjugate base is NO3 minus. And then base is F minus. Conjugate acid is HF. So these are the two pairs. These are the acids. These are the base inside your solution. Another important concept for this part is if you have a stronger acid, its conjugate base will be weaker. This is actually a very important concept because this is actually a stronger acid than this. So its conjugate base will be a weaker base. Therefore, if you just consider the basicity, the F minus will be stronger than your NO3 minus. So these are the two rules you should always memorize. If you see a chemical equation with single error, then you should be able to predict which acid is a stronger acid. But if today you have a stronger acid, its conjugated base will be a weaker base. So those are two things that you need to memorize